Good afternoon. Thank you all for attending this talk virtually. I'm Letitia of Fast Labs BA Systems in Burlington, Massachusetts. Today I'm presenting our work on supporting verified parser development with ACL2 for users without extensive formal methods training. This work was developed with my colleagues Greg Ekman, formerly of BAE Systems, and Elias Garcia and Sam Atman of Special Circumstances. Our approach uses a two-step process to parsing a document in terms of syntax and then checking its semantic properties, both based on a user-defined format grammar in the spirit of LangSec. We demonstrate this approach specifically on PDFs, which we've been studying for DARPA SafeDocs for the last 2 years. As we've learned, PDFs are a complex file format specified by an ever-changing standard, which has already exceeded 1,000 pages. They've been demonstrated to be capable of executing embedded malicious code, having their encrypted contents disclosed without decryption, and in recent news, researchers have also demonstrated how the content of signed PDFs can be modified and still show up to be signed. Violations of the PDF standard can also cause crashes, faults, and display errors, depending on the PDF reader. So next, I'll discuss the structure of PDFs to show the challenges of ensuring that they are free of flaws. So PDFs are composed of 4 sections, as we can see on the left. The header consists of a tag PDF and the version number, while the objects contain the content of the PDF that we see. However, not all of those objects are in use. The xref table references objects which should be displayed, and the objects form a tree as shown on the right, with a catalog object at the root, which references the page tree node root, which in turn references pages, or another page tree node referencing other pages. A catalog object also references the outlines, which is the sidebar you can see on some PDFs with links to each of the sections. A PDF needs to be checked for its syntax and semantic properties, where by syntax we refer to, for example, the correct format of every object to start with an index number, then 0 and obj. But a syntactically correct object can, however, reference itself in a cyclic reference, as shown in purple, or a page tree node object could refer to a non-existent object or object of a type which does not belong in the page tree, as shown in red. And all of these are violations of the PDF standard. These are what we refer to as semantic property violations. All of these rules are declared in the PDF standard on each type of object, such as required attributes and type of objects allowed to be referenced in that field. These have been structured in a data object model, which can be used to systematically generate semantic rules. So we want guarantees of correctness on the created syntax parsers and semantic validation functions. And formal methods offers greater assurance than unit tests, as it catches corner cases humans can miss and provides mathematical proofs that can show that the system meets requirements on correctness, security, and so on. However, formal methods is generally difficult to learn and could be daunting for developers due to the steep learning curve. While some verification tools use a push-button approach to generating proofs, ACL2 is a proof assistant and requires user interaction, as I'll explain next. For those who aren't familiar, ACL2 uses first-order logic and is based on a subset of Common Lisp, which is a functional programming language. Users write functions and then theorems about that function, which the proof assistant tries to prove automatically. With experience, users can offer hints to guide and speed up the proof process. The example here shows a function we had to write to check if a string is a member of a string list. It acts recursively by checking if the string is the first member of the list, referred to as car, as we can see in the ACL2 terms, and then passes the remainder of that list, as we can see here with the CDR of string list, back into the function each time. So the correctness of this function will be proved by induction, as I'll show later, and the first step is to confirm that this function returns true on the smallest case, or base case, which is checking that if string X is a member of a list with just itself, as is shown in this theorem. We can then use these functions and theorems in ACL2 to create our verified syntax parser and semantic validator. I'll first show how we generate the verified syntax parser in the first stage of document analysis, which should be the equivalent of an existing parser in a more usable common programming language, like the hammer-based parser in C, which we use for safe docs. So here's one example of parsing one section of a PDF in ACL2. So to parse an xref table, as shown on the left, we first check that the table starts with the string xref, and then we parse for the next line a 0 and then the number of entries. And then to parse each line, we first parse a number, which is the offset of the object, then the space, then another number, which is the generation number, and then the string n or f for whether this object is in use or not. If the object is in use, then we save the byte offset of the object to be parsed, and if it's not in use, as we can see for this first line, we don't have any objects to be parsed. And then we parse the next line and save that offset as an entry as it is in use, so we can see here. And then we parse the third line. And as this line is also in use, we also save that offset. As we can see, parsing the xref table can be broken down into separate functions, parsing each line or element, and each of those functions can then be broken down into the base functions of parse number, parse string, and so on. We can then write theorems about each of the base functions, such as parse number returning a number if given a string of digits, or parse string returning nil if the start of the text is not the string to search for. And we can then build up different verified parsers from these verified functions. So not only could we, for example, parse the objects list of PDFs, which consists of strings and numbers, we could also parse different document formats as long as they could be built up from these base functions. So after syntax parsing, we perform semantic analysis on the resulting abstract syntax tree. To generate equivalent semantic checks in C and ACL2, we rely on rules written in a meta-language. So we call our meta-language tower as it builds upwards from lower level expressions. So show equivalent C and then ACL2 code are generated from the rule file expressed in tower X expressions. So here's one example. Our running example is going to be the rule here, that all objects referenced by the kids field of the page tree node objects are of type page object or page tree node. And here we show the tower X expressions broken down into partially into the for all expression, and then finally the string member expression that those objects are either of page object or page tree node. And then we also generate automatically the associated function and proof pattern in ACL2, where the lowest level expression's ACL2 function, child type check, is a simple Boolean check. And then the for loop expression's ACL2 function, child type iterate, applies that Boolean check to each element in the list, structure that should be familiar. And it should return true only if all of the checks return true. And then we fill in the ACL2 function definition that the lowest level tower expression checks if the string type of an object is a member of a list of these lists of strings. And the proof is just a trivial restating of the function. And the for loop expression applying the Boolean check on each of the objects in the list of objects is, as we can see, the recursive function. And its proof is a proof by induction that I've previously mentioned. So proof by induction requires a base case, an inductive step, and conclusion as shown here. So as before, the base case applies to the smallest possible case where the list is just that one single object, and the child type iterate, and that child type iterate should return true on this list of objects if child type check return true, checking just that object. And then the inductive step shows that if the Boolean check is returned true on the first member of the list, and the child type iterate return true on the rest of the list, then we should return true checking the full list. So this proves that if the check succeeds on the full object list, it must have succeeded on each individual object as stated in the conclusion theorem. So as we note, this proof by induction is independent of the actual properties checked by the lower level child type function. We only need to know that it returns a Boolean. So that's the advantage of Tower, that the expressions are independently modifiable, and we can easily create additional rules without manually writing more proofs. For example, here we want to write that object numbers must be within a certain range, or the range of allowed integers. And writing this new function only requires changing the lowest level checker function by generating it from the Tower translation. And this does not touch the proof by induction for the next level proof or any of the other proofs. And for additional convenience in writing rules, we also generate them automatically with a graphical user interface, structured based on the PDF object structure. So we can see the graphical interface contains a name for the rule, and then follows the structure of the PDF semantic objects, as it has a type where we specify that this rule applies to page tree nodes. And then there's a Boolean check on the attribute dictionary. For example, here we are checking that all of the objects are referenced by the kids field must be of type page object or page tree node. So our final framework is shown here, where rules expressed in Tower meta language can be written by hand or generated in our convenient graphical interface. And then those rules are passed to the generator by automatically building equivalent C functions and ACL2 functions and theorems. The abstract syntax tree previously generated is then passed as input into the semantic validators to ensure that all of the semantic rules, such as from the PDF standard, were satisfied. With our approach, the advantage is that once we've written all of the base functions for each Tower expression and the associated theorems, the developer only needs to write the new rule in XML or in the graphical interface, and that requires no interaction with the ACL2 proof assistant or real understanding of formal methods. So as part of DARPA SafeDocs, we tested our Tower-generated semantic validation functions on provided flawed PDFs. So for example, here we identify that this PDF violated the rule in our running example as the page tree node object. Object 2 references object 3 in its kids field, and object 3 is of type struct tree root, which is not one of the allowed types. And another semantic violation we detected in this PDF was that this additional page tree node object, object 6, was missing a count field. As we remember from the PDF standard or the object model, this field is required. So in conclusion, we've demonstrated how the Tower meta language is used to build equivalent, performant, and verified functions for syntax parsing and semantic analysis for secure parser development. Our meta language allows developers to write verified semantic functions by breaking them out into independent expressions for flexible modification and replacement. And most importantly, once we've written the translation, we don't need to continually write proofs with the ACL2 Proof Assistant. So through SafeDocs Phase 2, we'll consider how to apply Tower to additional file formats besides PDF, increased automation in generating both the UI and base expressions based on the grammar, and then full generation of an equivalent syntax parser, all to better support the language theoretic security approach to safe and secure parser development. And with that, I'll take questions.